So why don't we get started? It's my great pleasure to introduce José Correa as our ORIE Colloquium speaker today. José has a long list of, impactful publications and distinguished contributions. Most recently, he did some award-winning work on school choice for Chile. And today he's going to talk to us about apportionment through multi-dimensional apportionment through discrepancy. So take it away, José.
Thank you, David. Thank you for the invitation. It's a pleasure to be here. So yeah. Would have been nicer to be there, but I guess Omicron, it's not making travel possible these days after already 2 years without traveling, but anyhow. So, okay, so I'll tell you about some recent work I've been doing, and this started a couple of years ago after in Chile it was decided that a new constitution has to be written, and there were some new requirements that are related to what I'm going to talk, which is this multidimensional proportionality, and this is based on joint work with my former master student that's now doing a PhD at TU Berlin, Javier Sembrano, my former PhD student, Victor Verdugo, and a current master student that's doing, finishing his master's now. So it's based on 2 papers, and I can send you copies of these papers if you want to, or you can probably find them online as well. So, okay, so let me get started. The basic question is how to elect a body of representatives, say a House of Representatives, a parliament, or whatever. And there are, of course, zillions of systems, and we often say that there are as many systems as democracies in the world. And actually, there are more systems than democracies because even each democracy has more than one house, and each house has different method, a different method for the election. But in any case, we can roughly group electoral systems for House of Representative into four methods, and actually 3. So one is typical majoritarian systems, such as first past the post in the US, and this is used throughout the world in many places, France, Brazil, Canada, etc. Another big family is what's known as proportional systems, and the main difference in proportional system versus majoritarian systems is that each district gets many seats, and these seats are allocated in proportion to the votes of each of the parties. So this is a proportional system, and this is what we have in Chile, in Israel, Spain, and so on. There are some countries that have what's known as mixed proportional representation methods, in which part of the house is elected through a proportional system, and part of the house is elected through a majoritarian system. This is the case of, for instance, Germany is a typical case for this. And there is one more method which is different, substantially different from this, which is known as the biproportional system that's used in most cantons in Switzerland, in Zurich in particular, and which I will explain in more detail. But basically, you mix both dimensions, right? You mix the political dimension and the geographic dimension into one pool. To give you an idea of what's been happening in the last, I think, 100 years in the world, there is this table by Colmer about 15 years ago that actually tells you how our system changes. So here, indirect methods are methods such as the House of Lords in England, methods that are not elected directly by votes of the people. And the changes go more towards proportional systems. So more countries are moving towards proportionality or mixed systems than to majoritarian systems. So this is a trend that's been, it's been seen in the last 100 years. Most democracies are moving towards more proportional systems. So whenever a country changes its system, it's more likely that you will end up with something more proportional. And there are good reasons for this. There are many established reasons for this. But this is more politics. I'm going to talk about more operations research than politics here. So let me first try to say why we want multiple dimensions. So The main reason for this, is that in this particular election in the Chilean Constitutional Convention that was elected a few months ago, like a year ago, it was imposed by law that not only you have geographic representation, political representation, but also that it has to be paritarian gender-wise. So half of the Constitutional Convention had to be men, half had to be women. And this adds a new dimension. And there are other examples of dimensions that go beyond political and geographical. And there are not too many examples in the world currently, but there are others. One example is New Zealand's parliament, where Maoris have representation. Another example, which I don't think it ended up being an example, was the Federation of Bosnia and Herzegovina, where it was proposed to have some paritarian ethnical representation in the parliament. And the question is whether more dimensions are going to be important in the future, given the political representation crisis that we're living in many countries, in particularly in Chile, but I think it's not unique to Chile. This. Okay, so given that we wanted to have some multidimensional multidimensional representation, the question is how to do it. So we had this new election to come. We had to design a system to elect a House of Representatives with a certain number of people per district, a certain proportional representations according to parties, and also paritarian in terms of gender. So why not following the idea of proportionality? So what is proportionality? Let me try. In one dimension, this is very easy, and I'll quickly tell you what a proportional system in one dimension does. So let's say we have one dimension. We want to allocate a number of seats, H, proportional to the votes of the lists. Let's say we have 4 lists in this example. No, 3 lists in this example. They have 43, 34, and 23 votes. Okay, so let's say this is our vote vector, right? And we want to allocate 10 seats. So what would you do? Like the typical thing you would try, I guess, is you would try to scale this vector. So you multiply you would note that my example was very well cooked so that the entries add up to 100. So you multiply by 0, 1 every entry, and you end up with this vector here, which is nicely proportional to the original vector. Nicely, the entries add up to 10, but the typical problem that you have here is that the entries are not integral. So this is a fractionally proportional solution, and is unique in many ways. So what do you do to make it integer? And for this, we go back to Jefferson, and Jefferson already came with the idea of what is called divisor methods. So let me start with this equivalent view here. So in the equivalent view of a divisor method, what you do is the following. So in the US, to allocate the number of seats for states in the House, you use a very similar approach. You use what is known as the Huntington method, not the Jefferson method, but the Huntington method. The Jefferson method was used in the US until, I don't know, I think 1930s or something. So what you do is the following. So you take your vote matrix, and now you look at the largest number your vote vector in this case. So you look at the largest number, and you greedily start allocating seats. So I allocate 1 seat to this guy, to list 1, right? And now, in the next iteration, what I will do is that I take I take all entries and I divide them by the number of seats I have assigned so far plus 1. This is the Jefferson method. So my new vector will be 43 divided by 1 plus 1, 2, 21.5. And the 34 and the 23, I just divide by 1, so 34 and 23. So now I look at the largest number here, and I realize that it's the 34. So I assign a seat to list number 2. And now I continue doing the same thing. I follow this process. So I now divide again the first number by 2, the second number by 2, and the third number by 1. I look at the largest number. This ends up being the last one. I assign a seat and continue and so on until I allocated all the seats I wanted to allocate. In this case, it's 10 seats. So we end with this vector. Okay, so the formula here can change depending on the exact method we're thinking. Jefferson methods does this. Webster methods does something slightly different. Cool. But this is equivalent to the following. It's equivalent to the following, to say, you know what we are going to do is go back to the single dimension, to the fractional method. So we want to look for a multiplier lambda. We're going to multiply every entry of our vector by lambda, and we will round down and make sure that the entries add up to 10. So, for instance, in this example, we could take lambda equals this number, 0.1117, multiply every entry, round down, and get the same vector. And these two views are exactly equivalent. So this is the same thing. So you can actually prove that you get to the same outcome. And this method, which is known as Jefferson's method or Don method in Europe, is widely used to allocate seats for districts or for parties or in many different contexts. So this is a well-established notion of proportionality when we need integrality. Cool. So now what about in 2 dimensions? Now the situation is not so obvious, I think, even fractionally. So suppose now that my vote matrix, my vote vector is actually an aggregate vote vector, and it was coming from 2 districts. So in district 1, we had this 28, 23, 14 votes, and in district 2, we had 15, 11, and 9, and each district needs to get 5 seats. So these guys, each district gets 5 seats. The number of seats a district gets typically in most systems is sort of proportional to the population, or under some additional constraints, like you don't want districts to have less than, I don't know, 2. In Chile, we cannot have a district having less than 3 seats, for instance, even if it's very even if its population is very small. Okay, but then these are fixed typically by law. So how many seats you get in each district is typically fixed by law. And in this case, we would compute this proportional allocation, and we would say that the marginals on the rows, on the party sides, would be 5, 3, and 2. Because this is what our aggregate vector tells us, right? So in most systems, you would run separate elections, one for the first district, one for the second district, and see whatever you get there. But when you have many districts, and then all these errors start to add up, and you end up having large errors in the end. So now we don't want this. So we're now looking for a new matrix that is proportional to the vote matrix, but satisfying that the marginals are exactly what they have to be. So 5 and 5 for every district, and 5, 3, 2 for the parties. What is the solution to this method? The solution to this problem? The solution actually is pretty much well established. So what is a proportional matrix to be? The solution is to find multiply. Sorry, if there are questions.
Quick question. You also take the floor there, right? Votes times that. Do you take the floor?
I will take floor. Yeah. I will take floor in a little bit. Now I'm thinking about fractional proportionality only, right?
Okay, thank you.
Mm-hmm. So now I want to define a fractionally proportional matrix that satisfies some marginals. Yeah. So what is a fractionally proportional matrix? That's the problem right now, and I will switch quickly to the other problem, which I do want integrality. Yeah. Thank you. Yes, very important. So we're looking for this matrix, and the solution method it's actually find multipliers, lambda i's and mu j's, row and column multipliers, and such that your new matrix, which is going to be the vote matrix times the multipliers, so the entry ij of the vote matrix is going to be Vij times lambda I times mu j, and you want that this matrix satisfies the margins. This is what you want. Cool. And this is actually a relatively well-established solution concept for proportionality of matrices. It's nice that it always exists. It can be found efficiently. It is very related to a problem known as matrix scaling that appears, for instance, in transportation. I was talking to people in the morning, and there was this, how do you estimate an OD matrix in a city? So that's a typical question in transportation. When you have cell phone data, this is maybe not so hard, but suppose you don't have cell phone data and you just have like metro card data. How do you estimate your origin destination matrix? And typical thing is that you know the marginals, you know how many people travel from each zone of your city. So you have zones in your city, you have how many people travel from each zone, how many people get on a bus in a given zone, how many people get off the bus in a given zone. So you have your marginals, and maybe you can do a small sample and create a small matrix, which is an OD matrix of some small sample of your population. And now you can scale it using this proportional method. So this is typically done in transportation. It's known as Furness method, and it's been used for many years, I think. So it's a relatively, I mean, there are some fantastic algorithms and very complicated ones, and particularly Avi Wittgerson has worked on many of these things in the last few years. Okay, and another cool thing is that this extends to multiple dimensions. So people do this in many dimensions, so no problem. And actually, we can actually give a sort of an axiomatic perspective. This method, so the method of finding lambda multipliers such that the new matrix satisfies the marginals, is the unique method satisfying three very natural axioms. One is exactness. So if there is a single scaling factor, this is what you should use. Consistency means that if you restrict your solution to some rows or some columns or whatever, then this solution should still be proportional to what it has to be, right? And and then it's homogeneous in that if I scale the matrix, then things are the same. Like if I scale the matrix but I keep the marginals, then the solution has to be the same. And it's the unique new matrix that satisfies these three axioms. So I mean, this is, I think, a well-established solution for multidimensional proportionality. So, but then, I mean, Oktay, now questions kicks in, and what about integrality? I didn't say anything about integrality. So in 2 dimensions, this was done by Balinski and Demange in the late 80s, and they prove that you can always find an allocation which is given by, you take the entry of the vote matrix, you multiply by a row and by a, so you multiply by a row and by a column multiplier, you round down, and your new and your resulting matrix, which in this case is XLD, satisfies the marginals and it's integral. So it's guaranteed to exist under very mild conditions that I don't want to discuss here. So cool. So in 2 dimensions, we have this notion of biproportionality. So we find these multipliers, row and column multipliers, we round down, and we make sure that the marginals are satisfied. And this can be done. Okay, Oktay, I mean, I'm not sure I'm answering your question now.
Oh, yes, definitely.
Thank you. Thank you. Okay, so let's think of the example again. So we have this matrix. We now find these multipliers. The multipliers, of course, are not unique. Not even in 1 dimension is unique, the multiplier. What is unique is the outcome, right? You multiply, you get some fractional matrix, you round it down, and you make sure that the marginals are satisfied, and this is the solution. There are many multipliers that do the job, but what actually matters here is the outcome of the rounding process, right? And now if you, well, you can actually check that all marginals are satisfied and so on. Cool. So one way of approaching this problem, which is not the original way, is the way basically started by Rothe and Zakaristen, is to write this, how to find this new matrix as an integer linear program. So you write an integer linear program with additional variables, which basically, so these y, l, d, t variables indicate whether you're going to pick the next. So you have where you pick the next seat. So all these variables are 0, 1, and the number of seats you will allocate are equal to the sum of these guys. And these variables, you will allocate them in the order of votes to n. So this is like inspired by the initial method by dividing by the number of seats I have allocated by 1. So if you look at here, I'm minimizing. So I always assign first the variables with lower index t. I'll always spend my LP solution first on those variables. I mean, the intuition is not so trivial, but you can, I mean, you can work it out. And the cool thing is that now you can prove that X is a biproportional apportionment if and only if there exists a Y such that XY is optimal for the linear relaxation of this problem. And the fact that the linear relaxation works here is because you have matching constraints, basically. You have only row and columns constraints. So it's totally unimodular and things are nice. So you always have an integral solution here, and this is your biproportional apportionment. Good. So what if we go to 3 dimensions or more dimensions, right? I will mostly talk about 3 dimensions, but everything goes to d dimensions, doesn't matter. So in 3 dimensions, what I want now is the following. I want the matrix X, LDG now, G for gender. I want that the marginals are satisfied in each party. So each political party, each district gets the right number of seats. And I also want that each gender gets half the seats. Or it could be some other marginal, it doesn't really matter. But let me just make it specific. So I'm here assuming half the seats. I want to find multipliers. I want to find multipliers. So this is the natural fractional proportional solution. I want to find multipliers, multiply each entry of the matrix by the right multipliers, the corresponding multipliers, round down, and satisfy these marginals. So I want to know whether this is possible. So these are going to be the entries of my matrix in the end. Okay, so bad news. We cannot guarantee existence of a three-dimensional proportional apportionment. And it's fairly natural that when you go back to the LP, you can extend this fairly easily, but now you have a 3-dimensional matching problem. So, I mean, it's not going to work as easy, right? And even it's NP complete to decide whether a given instance has an apportionment and a 3-proportional apportionment. So, and this is naturally, again, a reduction from perfect matching in 3-part class. So, okay, it's unfortunate. However, this is not all. There are some good news as well. So these are bad news, but there are some good news. The good news, and this is what I think is our main result, is that if we allow deviations from the marginals, which are small, and well, you will decide by yourself whether you find this is small or not, but I will allow deviations on dimension 1. I'm going to call dimensions 1, 2, and 3. So let's say let's think this is political, geographical, and gender. And by a U1 is going to be an integer, say 1, 2, or 3, or something like this. And if I set up U1 to be 3, what I will allow is that in each party, if the number of seats it corresponded to this party was 25 in the house, then I will allow anything between 22 and 28. Okay, if a gender had 70 seats, because the house was 114 total, I allow 70 seats, and U3 is 6, I will allow anything between 64 and 76. Okay, so this is the deviation from the marginal I will allow. Now, if I have that the sum of the reciprocals of the UIs plus 2 is at most 1, so I have this formula here, then I have existence of a 3 proportional apportionment. So just to give you an idea, so look, if this condition holds, then there exists an X verifying that each list gets the marginal plus minus U1, plus minus U2, plus minus U3 in each of the dimensions, and it's proportional. So, and also that the entry of X in the cell LDG is equal to the multiplication of the vote matrix times the multipliers rounded down. So some numbers that do work, for instance, in 3 dimensions is 111, 014, or 022, or things like this. In particular, this extends to many dimensions. And in particular, it extends to 2 dimensions. So in 2 dimensions, I will not have this term here, right? And if I don't have this term, I can do 0, 0. So in 2 dimensions, it extends Balinski and Demange theorem, right? So I can do it without deviating. Okay, this is exactly what I was saying, and actually, I mean, you can extend it in many directions. So the rounding rule I'm using is rounding down. You could use other rounding rules, and it doesn't matter. So if you want to, like, for instance, Webster methods, if you want to use Webster method instead of Jefferson method, Webster method basically is normal rounding, like as you would round grades in school. I don't know. So if you are below 0.5, you round down. If you are above 0.5, you round up. We can do a different, an arbitrary rounding rule. We can have soft bounds, for instance, if you want that each gender gets at least 40% of the seats, that's also possible to do it. Arbitrary dimension, and the condition, you just add the same quantities over the different dimensions. What we don't know is whether this condition is tight. That's, I think, an interesting question. So the only thing we do know in 3 dimensions is that it is not possible to do 0, 0 k for any k. So you give me a k, say k equals 100, and I can give you an instance whether you cannot do deviations of 0, 0, and 100 in the 3rd dimension. But we don't know whether, for instance, 0, 1, 1 is possible. That, I mean, our theorem says 1, 1, 1 is possible, or 0, 1, 4 is possible, but we don't know whether 0, 1, 1 is possible or not. That's something we don't know. Okay, so we can also add the constraint to elect the top voted candidate. I mean, all these methods have, I mean, different perspectives. So if you use these proportional methods, you're not guaranteed to elect the top voted candidate in a district, for instance. That it can be that this person is not elected, but you can impose this as a constraint, and essentially everything works reasonably well. And the fact that it's based on integer programming makes it very flexible to add constraints and things. Okay. So what is the proof idea? Maybe even before the proof, maybe even before the proof idea, let me give you some perspective for those of you that have taught the combinatorial optimization class. So let me go back to that previous slide. So a typical exercise in combinatorial optimization is the following. So
There's a quick question.
Sure.
When you're saying that these points are possible, do you need to pre-decide which of these slack points you want to try and, like, is that a choice in the algorithm, or is it that?
No, it's your choice. It's the designer choice.
Okay, so you need to specify, I want to target 111, and then there is a particular
and then you will find it, and then the algorithm will find that. Yes.
Thanks.
Yes. Yeah, exactly. So and let me give the perspective of combinatorial optimization, which I think it's interesting. So a typical exercise would be the following. So I give you a matrix with fractional entries and integer sums per row and per column. And I ask you to round the entries to either 0 or 1, each entry, so that the marginals are satisfied. And I guess many of you know that this can easily, I don't know if it's easy, but this can be done. I mean, this is an application of max flow min cut, for instance, or assignment problems or so. Now, I give you the same problem, but instead of giving you a matrix, I give you a tensor. I give you a 3-dimensional matrix. I give you fractional entries, some zeros, some ones, and then some fractionals, some entries that are fractional. And you are allowed to move every entry that is fractional either to 0 or to 1. And you want to keep the marginals, which are now per plane, right? So per list and per district and per gender. And can you find the rounding of this? And the answer is no, you cannot. But if you have this condition that I wrote down here, you can. If you are allowed to violate these marginals by these quantities, you can. So this is like a combinatorial optimization view of the result, usually. And we don't know whether this is tight, so I mean, still there is room for improvement here. So what is nice is that the condition does not depend on the size of the problem at all, like, or what are the entries or things like this. So it's just that it's just some fixed numbers, like universal numbers. Cool. So, okay, so what is the proof idea? So the proof idea, I think it's quite nice in the sense that, I mean, it's the LP is ugly, but it's a natural extension of the 2-dimensional LP, in which you have this multidimensional matching problem on the ground. So unfortunately, you don't have integral solutions, but what we will do is the following. We will take the solutions of the relaxation of this integer program, and then we'll use iterative rounding. We'll use iterative rounding to round this solution. And how do we use iterative rounding here? So what you do is the following. I mean, don't even read this thing. It's a bit crazy, but what you do is the following. So you first look at all the fractional entries. I mean, the integer parts of the entries that I got, then I'm happy with those integer parts. I'm not going to play with those. I'm only going to play with the fractional parts. So for the fractional parts, the fractional entries that I have to decide what do I do. I mean, what I will do is the following. I will look at only these fractional parts. I will look at the matrix containing only these fractional parts. And I will look at lists, districts, and genders having more than UI plus 2 fractional entries. So I will look at the districts that has more than U2 plus 2 fractional entries. And I will look at the sub-instance, so the subtensor that contains only these elements. So these lists, these districts, and these genders. I mean, gender, and now I'm thinking that there are many genders. No, that's not the problem. So this is a situation. And now you resolve you fix the marginals to what they should be for these entries, and you resolve your linear system as you would do in iterative rounding. And you prove that you have more variables than inequalities, so at least one variable will become integer, and you just iterate. And you just iterate. And you iterate, and in the end, what you have is that all parties, districts, and genders have at most one UI plus 1 fractional entries. Yes. You just take all these fractional entries and round them down. For instance, I mean, you actually do whatever you want, but you say you round them down, all of them. And as all these entries were fractional, but they were adding to an integer, when you rounded them down, you at most deviate by U1 and not by U1 plus 1, right? Because they were adding, you had U1 plus 1 fractional entries that they were adding to an integer. So this integer cannot be more than U1. So that's where you save an extra one. So why do you have more variables than constraints? It's the typical pigeonhole principle argument. How many constraints you have? So number of lists in your set with more than 1 + 2 fractional entries, number of districts, plus number of genders with this property. By pigeonhole principle, this is not more than, each of these is not more than the number of fractional entries divided by the corresponding deviation plus 2, which was your condition, right, to enter the set. And this is at most the number of variables. Cool. So in each iteration, you fix at least one variable, and we're done. And we're done. Now, in the last step, we're not very clever in the rounding. Maybe there is a clever way to round in the end that can save you more in some dimensions. So this is very typical. I guess the first application of this is Beck-Fiala's theorem. One difference with Beck-Fiala is that, or discrepancy theory in general, is that we are controlling different deviations in different dimensions. And the typical thing you do here is that you would control the maximum deviation all over. So in this case, we would say in 3 dimensions it would be 1 for us, right? But now we are a bit finer in controlling, like being able to say we can do 0, 1, 4, so 0 in one dimension, 1 in another, 4 in another, and it results in something that actually works out. Good. Let me. I don't know if there are questions at this point. It's a good point to take a couple of questions.
So, Jose, can you say exactly what you mean with tightness in this particular case? So you said a couple of times that you're not sure that is tight.
Yeah. Okay. Very good. Excellent. So yeah, very good question. So this is my result. So my result is that if U satisfies this, then there exists an X such that blah blah blah. Mm-hmm. Okay. Now this condition is best possible only like think of dimension 3. So I'm only going to think about it's best possible only because I know that if I take U1 equals to 0, U2 equals to 0, and U3 equals to 100, then there does not exist X such that blah blah blah. Okay. Mm-hmm. But so this condition is satisfied by some vectors, but it's not satisfied by some other vectors. What I'm saying is that I cannot prove inexistence for all vectors that do not satisfy this condition. Right? I can prove inexistence only for a few of these vectors. Actually, only for this vector. Only I know that the 2-dimensional. I mean, the thing is that I know 3-dimensional doesn't exist in general, and I do know that 2-dimensional does exist. And the way to prove it is this example, which is complicated, but so you extend to one more dimension and you realize that you cannot do it. But it may well be that there are tighter conditions. So here I say, like if I allow deviations which are 0 by party, 1 by district, and 4 by gender at most, then I know I will always be able to find them a 3-proportional apportionment. Okay, but then maybe some other people can tell me, yes, but you know what? If I allow deviations which are 0 by party, 1 by gender, and 1 by district, so instead of 0, 1, 4, you have 0, 1, 1, then also it exists. I cannot prove this person wrong. Right? Okay. So it's not tight in that sense. Good. Thank you.
One other question about the particular form of instance that you're thinking of is based on the allocation across each category. But one thing we know about each of the fractions is that they lie on a lattice. Like we know the total number of people who are voting. Do you think you can get an improvement in that sense? That, like, I know the fractions cannot be arbitrary. I know they are some rational number.
Yeah, but the fraction, I mean, that's true. I know that. I'm not using that information. But if the vote matrix is, I mean, if you have kind of many votes, probably not much you can, but maybe for electing smaller, yeah, no, that's true. Like maybe if you want to elect a committee in some smaller election, then you can use this information, right? Yes. Yes. Or you want to elect, I was telling Katia, you want to elect the MOR board, maybe you can, you have fewer votes. I don't know. Anyhow, so okay, so let me tell you some of the results and in the 10 minutes or so I have left. So the story is a little bit like this. In October 2019, there was this big demonstrations in Chile. You probably learned of them. Some people had, I mean, we canceled conferences and many things after those months, and well, whatever. About a month after the main outburst was this peace agreement, in which this is our elected president now, Gabriel Boric. There was this peace agreement in which, like, most political forces, not all of them, but most political forces agree on writing a new constitution, and this was like sort of a way out of the problem. The election took place in May, and the Constitutional Convention has been working since August, I think, July or August. There was vast support for this initiative, like basically changing the constitution. There was a vote for that, and changing the constitution was approved by 80% of the people. So it was like pretty large support for this initiative. And this Constitutional Convention, by law, had to be paritarian in terms of gender. So this posed the question, the method that was elected, I mean, the method that in the end was used it's a sort of a greedy method. So in Chile, we have a proportional system by district. So we have separate election by districts. Each district gets a number of seats, which is a number between 3 and 9. And then the election was, I mean, we used Jefferson method to allocate according to how many votes each party got. And the method was the following. So you just run the election normally. If you get more men than women or more women than men, then you would take the least voted men in the district, and you would replace him by the most voted woman of the same party. That's the method. It's a greedy method. That's it. Very simple. What is, I think, the most interesting part has nothing to do with my paper, is the following, is the fact that by law, the Constitutional Convention had to be paritarian, then translated into having more votes for women than men. So in the election, there were more votes for women than men, and actually the paritarian method, so this correction, favored men and not women in the end. So this is something like mind-blowing to me. I mean, in the last election, in the last parliament, we had something like 25% women or something. And this was like, it should have been more than 50% women. Just by declaring I don't know, like, I don't understand it very well, but anyhow. So now this was a crazy election with many candidates, like many organizations came with their candidates, which were not political, but they were organized into lists anyhow. And we will compare. I mean, I want to show you some quick results on comparing the 3 proportional methods with the method that was used, which is a standard by district proportional method. 138 seats in total. The convention is actually 155, but there were 17 seats that were allocated differently. So it's actually 130. Okay, so the methods I will quickly show you are biproportional methods, which is essentially but by gender. So basically, this is, if you want, the first method is essentially the Constitutional Convention method. Right? Then the three proportional method, the three proportional method with a threshold. So many systems like Germany, Turkey, and so on, they have a threshold for representation. So 5%. If you don't get 3% or 5% of the votes, your party is not represented. So then we have and that's one of the methods we try. Then we have this plurality constraint. That's another interesting constraint. So you add the constraint that the most voted candidate in a district has to be elected. So that's what I call TPP. So it's three proportional method with the plurality constraint. There are 28 districts in Chile. So this does not fill up all the seats, right? It's important. And finally, plurality and threshold. Both things at the same time. So this is the fair share of votes per list. I mean, I can tell you what some of the lists are, but not all of them. This is the result of the Constitutional Convention. I mean, the numbers are small, but you can, I mean, there are some serious, like the blue party gets significantly more. But what I think it's more striking here is the green part here. The green part is the Green Party, is the ecologists. So the ecologists got 4% of the votes, and they got 0 seats in the Constitutional Convention. So here they have 0 seats, 0. And in any reasonable system, if I'm allocating 140 seats and you get 4%, you should get something, right? And well, in any of the proportional systems, they get 5 seats. So, and they're not below the threshold, unless they would be below the threshold. Whereas in the Constitutional Convention, there are many small, but much smaller forces, which are locally, I mean, there is this tension between local representation and global representation. So the Ecologist is a party that has a reasonable, small, but reasonable support across the country, the Green Party, whereas some of these parties are just very local movements, like movements, social movements that are extremely local and that like basically don't look at the rest of the country. And these guys, there are like 10 seats allocated to these guys in the Constitutional Convention because of the method. Whereas if you look at the three proportional method, this would be a much smaller number. I mean, only a few of them. If you add threshold, then less of them. I mean, then if you add threshold of 3%, then all of them disappear right away, just because they don't have 3%. And if you add plurality and 3%, some of them reappear. Because many of them are first majorities in their districts. I mean, they're strong local movements, right? Okay, so this Gallagher index is some measure. I mean, it's basically the Euclidean distance to the fair share. So some political measure for like how close are you to a fair share. And of course, and this is very natural that happens, of course, methods which are global, like all these T methods, all these three proportional methods, have much better global Gallagher index than these methods which are just local methods, right? But if you move into the local, like if I do the same calculation, so I look at the fair share in a district and I compute how many seats each party got in that district, then I get that the local methods perform much better, of course. So the trade-off that this global methods, the three proportional methods will take is that they will allow to deviate, to distort the election in a district and in another district so that the globals stay proportional, right? But I mean, that's a natural trade-off that you need. This is a pictorial view of this Gallagher index by district. So it looks much uglier when you look at three proportional methods if you do the plot by district, but if you look at it universally, then it's much not. I mean, if you look at the plot for the whole country, then it's much closer to the the global representation, to the fair share. And this is an interesting result. So one thing we do is the following. So what happens if you perturb the results, like if you perturb the votes? So we take some small perturbations of the votes, and we compute how many seats change from one party to another. So we take the same instance, we perturb each entry of the vote matrix, the votes of each candidate, if you want, by some small number, by some random vector, random like number, and compute how many seats change. And it's natural, but what happens here is that, of course, local methods, so CCM, the method of the Constitutional Convention, is much worse. So there are many more seat transfers because it's local, so that's natural, than global methods. And among global methods, what happens is that the 3% bound helps you to make it more stable, and plurality does not help you. So adding plurality makes more, it's easier to change the first majority by doing a perturbation, right? So these are like the two natural conclusions here. But anyhow, so these methods seem to be fairly stable in terms of that random perturbations of the votes would not change much the results of the election. And maybe the last thing I want to say before I finish is that there is one thing that's very important. In Chile, we have like very different voting power depending on where you live. So there is, and it's not even because of gerrymandering, it's just because we didn't change the seats allocated to any districts in like 40 years or something. And people move, right? And then you have these minimums, and so you have at least three representatives of the Aysén region, and there are very few people in Aysén. So a vote in Aysén, it's like 6 times more valuable than a vote in Santiago, for instance. If you have a global method, like a triproportional or a biproportional method, this problem, is somehow diminished by the fact that your vote counts towards the party through, equally, independent of where you are in Aysén or in Santiago. So it's a way of fighting against malapportionment, I think, and it's a natural way of doing it. But I guess the main conclusion is that using OR, linear programming, algorithms is actually a good tool, and as societies become more complex, I think the demands will become higher. Methods are complicated, but in the end, even with the current methods, most people don't know how they work. And I guess if you have some reasonable outcomes, it's possible to convince people and politicians that there are better ways to represent the people in a society. So thank you.
Thank you, José. Very nice talk. And we nicely have time for questions. So please, people fire away.
José, first, maybe a big picture question. Are there non-existence results that say, that there does not exist a way to make people happy? Because in all of these things, these fudge factors that you put in the UIs, they would just move the argument to what should the UIs be, I think.
So if I have my deviations, you mean people will complain that they don't know in which way I'm not sure I understood the question.
I think that my comment is, theorem, people will complain. So question, does there, like along the lines of your axiomatic development, are there a set of axioms that will be violated no matter how you do the rounding?
Yeah, no, I don't know. But this question about people will complain, I think there is some evidence, at least. I don't know, I'm not an expert in political science, but I think there is some evidence that parliaments that are closer to the people of the country make decisions which are less disputed by the people. And I think there is evidence, like relatively serious evidence about this. So my basic message is that you should try to make your House of Representatives to be closer to the sentiment of the people that live in the country. And if this happens, maybe naturally things will be better. But I agree that people will complain in any case, right? I mean, of course, otherwise we wouldn't be people, right?
Nikhil, go ahead.
Really nice talk. So in various points, it seemed like different methods prioritize some dimensions over others. So I think like the greedy one would prioritize party over gender. Sort of, is there a natural way to impose like sort of ordering on the dimensions, or like some arbitrary distance function or something on the dimensions, or something that could emerge?
Right. Yeah. No, I don't know. And even in the algorithm. So when you solve this linear system, you could give priority to one or the other. So one thing I didn't mention is that in practice, in the three-dimensional instances we solve, so we ran many simulations with like even to change seats. We always, okay, this is the priority we set. We will not deviate in party. We will not deviate in district, and we will try to deviate only in gender. And I think we never got to deviating not more than by 2 in gender. So we never went beyond 002 in any of the instances we run. So now, what is the right priority? Yeah, I don't know, to be honest. Like what?
Yeah, I guess, the question is also like, I was wondering if there's a layering on top of the algorithm that like sort of that priority could emerge from the votes or something. Yeah, I'm not sure.
Yeah, it's more in the design, right? So when you design how much do you want to deviate, you make that decision. But yeah, it's, I guess, unclear.
Okay.
Hi, Andrea, you have a question?
Yes. Is there any other problem in which this deviation can be actually, with respect to discrepancy theory, in which this deviation, different deviation with respect to different, order of things can be actually useful?
Yeah, it's a great question, actually. I haven't encountered other applications of this, but I presume that there should be, right?
Yeah, it's very fascinating because in this classical discrepancy theory, you don't have this, right? You have this condition.
No, you just have one
over
D,
the
right?
rows of the rows of your LP in which you can play with. But I don't see any. I mean, it would be interesting to think about that, because I guess it's actually natural to think that the constraints of your problem may have different characteristics, right? I mean, in a certain sense, for you, is that there are 3 sets in the 3-dimensional case. There are these 3 categories. So these 3 set of constraints have different meanings for you, and then you can play differently with them, right? I mean, and,
exactly.
I think that would be very nice to have in other problems, to see if there is something that you can say.
Yeah, indeed. Yeah.
Are there any governments in the world that do a timeshare as opposed to a round?
Sorry, I mean, Shane?
Yeah, sorry, this is a wacko idea, but let's say that I got 0.5, you've got 0.5, 2 different parties. So I get someone who spends half the next term in Parliament. You put someone in for half the next term in Parliament.
Yeah, I mean, I've heard these ideas. I mean, also I've heard this idea of having fractional votes, right? Not everyone has the same power, vote power. But I don't know. I don't know. I'm not convinced by that. Typically, this is legally complicated. That's one thing. Another thing is that maybe the decisions that we're taking in the first semester are those are the important decisions, right? I don't know, like, and then discussions between people that have different voting power are also not very natural, right? I don't know, like, but that's yeah, definitely a possibility. Like you could have this kind of thing, and I don't know how will it work.
I guess
So one more question. Oh, sorry. Yeah, one more question. I was wondering if you can write an IP to check your theorem. I mean, your theorem is not if and only if. Can you write an IP to find an instance that will
We tried that, but it's not clear how to do it, right? Because you're looking for all the, I mean, the space you're looking, it's huge. All the possible examples that could be bad, right?
True.
So for each example, I need to prove that they do not exist multipliers, lambda mu, delta such that this property. No, it's not so. Yeah, I mean, to be honest, I think it's a great question because like having a good technique to prove lower bounds would be nice here, and we don't. So the only thing we have is like something we came up with like by hand somehow.
So I guess I'm also a little curious on the behavioral phenomenon of what happened with the election. I mean, was there a, I mean, to what extent can you attribute the success of women to the rule, to the—
Yeah, I don't know. No, that's amazing.
Yeah.
Yeah.
Candidates in anticipation of the rule, to the turnout of the voters in reaction to the, I mean, there are various layers. And so, I mean, it's hard to, I mean, presumably there's been some analysis done to try to understand the phenomenon.
Yeah, but I don't think too much. Like, I don't think people have asked this question. Like, so I can tell you one thing. So in the 2 parliaments ago, I mean, the same system is used for the parliament and for this constitutional convention. So 2 elections ago, we had like 20% women. And then there was a law that parties needed to put an equal number of candidates or an equal number of men and women candidates. And this improved the number of women elected from 20 to something like 30%. Okay, and this time, like you of course need to have the same number of candidates. So this stayed like this. But now they said, and now we're going to use this method to correct. In each district, we're going to use this greedy method, right? And it was like a game changer. Now it's like women got more than 50% of the votes.
But do you think people understood the impact of the rule? I mean, you know,
I don't know. No, I don't know.
I mean, yeah.
I know. I really don't know. Like maybe it's just like a bias that when you go for an election, you were used to vote for a man and say, oh, I vote for a man. And now some law is telling you, no, but you know what? Why? I mean, women are equally qualified for this job than men. So we're going to make it 50-50. And I say, oh, well, maybe I can now vote for a woman. I cannot explain it, right? But I think it's very surprising.
Well, I mean, if you play a game that you want your candidate to win, in this case, yeah, it's very natural to switch to a woman, right? Basically, because if you think your candidate is not the top one, I mean that if it's a man, they're going to be thrown out. So I think it's
but it happened the other way around in the end.
No, well, yes, but
people voted.
There's no equilibrium.
It's sort of a coordination game, right?
It's a game, yeah, exactly. Yeah.
You have to play it many times to settle.
Right. Yeah.
There were more women thrown out by the system, by the paritarian system.
Maybe that was the purpose of the system. Who knows?
No, I don't think that was the purpose. I mean, that just happened, right? Anyhow, yeah, I don't know, but it's very intriguing. I agree. Very interesting.
It's a beautiful rule compared to, so the version of this rule in India was that seats were actually reserved for women versus men. And this is kind of a more intriguing, like that is much more like a local quota as opposed to this kind of a like ex post quota versus an ex ante quota. And I mean, I think that would be an interesting comparison to see like what's the difference between doing a local on like ex-ante reservation versus an ex-post reservation. That seems to be the difference at a high level, which, I mean, it's a beautiful rule. Like,
right. So there was a proposal. Yeah, I can tell you that there was a proposal at the time we were discussing how to do it, to do 2 separate elections, elect 70 seats for men, 70 seats for women, and each person has 2 votes. 1 for men, 1 for women. But this was discarded for some reason.
We should let Jose have a moment to catch his breath before his next appointment. But many thanks for a great talk. And
thank you. Thank you. Thank you all. Very interesting discussion. Thank you.